Okay, thank you. Uh, Actually, you're seeing my Zoom in real life, so there is a little bit of a lag. I will try to cooperate with it. As the title suggests, I would like to talk about wearable robotics today. And here you can see two examples. On the top, you can see ankle foot orthosis. Ankle foot orthosis are used to assist the ankle joint, and there are passive, semi-passive, semi-active, and active examples of them. On the bottom row, you can see lower back support exoskeletons. And the issue, the dilemma with these robotic devices is, in order to add functionality to the system, we have to use actuators. And these actuators, they add complexity, they add weight, and they add cost to the system. So the end users actually don't end up using them. I've been going to the University of Tsukuba hospital for over 10 years now. And I've never seen a patient using an AFO that is semi-active or active. It's never been prescribed in front of me. It's never been used. Rather, most of them are using the ones that are here on the top left, the passive and the semi-passive ones. So in order to address this issue, we have to look at the actuator technology that is being used in these wearable robotics. On the left side, you can see passive devices, passive components. These are a compression spring or elastic band. These are lightweight. They require almost no upkeep, and they're compliant. However, they provide only low power. You cannot control them in any possible way, and they only offer store and release of energy or force. On the right side, you can see the active actuators. So there are two common ones. This is pneumatic artificial muscle, PAM. It uses air pressure. It provides high power. It's inherently compliant. But the problem with it is it requires high upkeep and cost. So you need to tether it to this giant compressor over here. You need valves and solenoids to control it, or you need a canister that is attached somewhere. The DC motor is great for industrial applications, but when you put it on the human, one problem is that it is rigid, and you have to use gearboxes with it. So that's an additional problem. And also it requires batteries. So the one that I'm most interested in is the second one over here. And this is relatively new. It's using semi-active components, semi-active devices in wearable robotics. And especially the one that uses smart material. For the one who is not familiar with smart material, it's a material that can change one or more of its properties under the effect of an external stimuli. So for example, the picture here shows a magnetorheological fluid. This fluid can change its apparent viscosity under the effect of an external magnetic field. These devices, they can provide moderate, sometimes high power. They are semi-controllable. But the major issue with these devices is they can only dissipate force. They cannot generate force, and they cannot store and release force to be used in a wearable robotic system. So what I propose is we have to combine it with something else. Just by itself is not going to be enough to break the loop. So what we did is we combined it with passive components. Namely, we combined it with a compression spring. And this way we harness the advantage of both types of actuators. So rather than me explaining to you the rationale behind this, I would like to use the words of Professor Shigeo Hirose. And he said that a mechanism is often thought of as simply as a motion conversion system that processes input motion and converts it into the desired form of output motion. Rather, it is more essential to be able to temporarily store, divert, and then release the power flowing from input to output. So this is my own translation, his original text in Japanese, so maybe some Japanese professor can translate it better than I do. But I think you get the idea of what he's trying to say. So we made a shopping list of sorts of a device, a semi-active device that we want to develop for wearable robotics. We wanted to be able to regulate its mechanical impedance. And we wanted to be able to regulate the mechanical functioning of the physical system. This is done through damping and braking. Also, we want to be able to store and release energy. This will be through the interaction of the clutching and the compression spring that will be used inside. We want it to be of a compact form factor. We want to have small size and small weight. We want to have low power consumption, so only uses a small battery to operate. We don't want to have gears or tethers, which means it's going to have to be designed to operate in the same speed and force range of the human body. And hopefully we want it to be a simple mechanism, one that is easily adopted in different applications. So we tried to design this kind of device, and this is what we ended up with. On the left side, you can see the component. We call it MR link. MR because it uses the MR effect, and link because it can be used as a link in a mechanical linkage system. It has a bobbin and an outer cylinder that are made of material with high magnetic permeability. There is a coil that is wrapped around the bobbin. It generates a magnetic field that runs through the bobbin, through a gap that has MR fluid to the outer cylinder. And the magnetic field running in the gap creates the MR effect. And then it has a compression spring that is embedded inside of it down here. And this compression spring is kind of sandwiched between the outer housing, the bottom outer housing, and the bobbin, and is constantly applying a force to push the bobbin upwards. So this sets an initial position for the device. And then whenever an external force is acting on the interaction rod from the top, it will compress down this spring, and this will store energy in it. And then we can clutch the location of the bobbin with the MR effect and kind of hold this energy for a while. And then we can release this energy by releasing the MR effect. We worked on this for a while, and you can see here like consecutive prototypes. And always what we try to do is we try to increase the power to weight ratio. So the power to weight ratio in this figure here is shown as Newton to gram. And only recently we were able to achieve values higher than one, meaning that we can provide more than 1 Newton per 1 gram of the device weight. So I'm going to show a couple of prototypes and comparison to a somewhat similar DC motor with a gearbox. So this one here you can see holding in the hand. It can provide 250 Newton of braking force and store and release force. It consumes only 3.3 watt. The DC motor consumes almost 30 watt. Its weight is 110 grams. The DC motor with the gear and everything attached to it is 800 grams. There's another one. It produces about 600 Newton of braking force and can be used as energy store and release force. It consumes 5 watt. The DC motor consumes 31 watt. Its weight is 300 grams, and the DC motor is 800 grams. So obviously, these devices are not active actuators. They cannot generate force by themselves. They can only store force from the physical system and later release it. So they're not equivalent to DC motors. But I'm going to show you how we use them in wearable robotics applications. So today I'm going to show 3 examples. One is an AFO, ankle foot orthosis. One is a back support exoskeleton, also made with the same device. And one is a training device for muscle training. I'm going to start with the AFO. First, I'm going to explain the condition it's treating. It's called foot drop, or sometimes drop foot. So in normal gait, there are gait phases, and there are different functions for the ankle joint in each phase. In foot drop, there is a weakening of the muscles, or an inability to control the muscles. So at the initial contact, there is an issue in loading the limb. There is no smooth transition from swing to stance phase. And during the swing phase, the toes are dragged on the ground. Both of these issues, they cause falls. We want to avoid falls in this kind of fragile population. So a robotic solution for this system, hopefully, would be able to provide some additional mechanical impedance at the ankle joint during the initial contact, and also would not impede the progress of gait during the stance phase. And during the swing phase, it would provide some force or some torque to lift up the toes to create some gap or clearance between the toes and the ground to mitigate toe drag. So this is the device that we designed. Simply what we did is we took the MR link that I showed to you, and we flipped it upside down. And then we connected the housing to one of the lateral bars of the AFO. And then we created an arm here in which the interaction rod can act on the ankle joint. And the functioning of the system is, at the initial contact, we detect that with sensors. And then we operate the MR link not to the fullest power as a damper to provide some cushioning for smoother transition from swing to stance phase. And then at the end of the initial contact, then we clutch the bobbin to store the energy that was held inside the spring and to create a free gap between the interaction rod and the foot segment. This would hold the energy for later, the force for later, and it will not impede the progress of gait during the stance phase. And then when we detect that the foot has departed from the ground, we release the clutch of the bobbin, and then the spring force acts down on the foot segment to provide a torque to lift up the toes during swing. We tested this with healthy people and we verified the functions. And then we conducted some end user tests at the University of Tsukuba Hospital. You can see the same gentleman in the top video walking with the plastic cast AFO and the bottom video walking with smart AFO. And you can see almost more than 2 times the speed of walking he was able to achieve with this AFO rather than the one he usually uses. So we can also look at the trajectory of his ankle joint during a gait cycle. So with the plastic AFO, you can see the trajectory is kind of shallow and it has a lot of variance. With semi-passive AFO, actually it improves a lot, but still the baseline is lower than the neutral position of 90 degrees. With the smart AFO, it offers an increase in range of motion. There is more clear trend in the trajectory and consistency in the trajectory as well. So second, I would like to show a back support exoskeleton made with the same technology. So we created a back support exoskeleton with 2 functions. One is to break the forward bending movement to ease the load on the lumbar parts and the hip joints when the person is holding a weight. And during this phase also, we would store energy inside the spring. And then during the lift up phase, we would release the spring energy to assist the user lifting up the weight. And as promised, the structure of it is quite simple. We just installed MR links on kind of a plate on the back, and then we connected them to the rotary hip joints with a Bowden cable. So this simple mechanism converts the linear motion of the MR link into rotary motion around the hip joint, and it allows the device to function as shown in this video. And we tested this. We tested the muscle activation while using this device. So in this figure on the left side, you can see pseudo lifting. Pseudo lifting means not really holding a weight, just performing the movement kinematically. And the gray bars are without the device. The dashed bars are with the device. And you can see with the device, actually this was no control, just like without current in the MR links. Nevertheless, it reduced the muscle activation and increased the symmetry between the right side and left side. The muscle that's being measured is the erector spinae left and right, and both of them reduced and became more similar. With actual lifting, the person was holding a 12.8 kilogram weight, and he performed the task without the device and then with the device activated at 40% of its power. And also in this case, the muscle activation was reduced and the symmetry between the right side and the left side was improved. Why the symmetry is improved, we're not really sure. Probably it's just because there is a mechanical linkage between the 2 sides when using the device. Also, we tested the assist performance with multiple subjects at increasing currents, and we found assist performance as high as 40%. This was made with experimental data that is inputted to a model of the user and the device. We had one issue with this one, the lift power. We did not have a lot of it because of poor fitting of the exoskeleton, but that was most probably because it's a handmade prototype that doesn't fit very well to the user's body. So last, just one slide, I will show we use the device also in muscle training. So you can attach it to 2 segments of the body, and then you can use it as an artificial additive force. Simply, you can activate the MR link to some power, and that will be equivalent to holding a weight and training with it. But this is just a digital device that you can control electronically, and it doesn't take much space or weight. So I will talk about what I think is some possible directions and applications of MR devices as well. So in our lab, we're also doing para-esports research. That is, we're creating gaming controllers and interfaces for persons with physical disabilities to play esports. And then we thought to ourselves, well, that can also be used in telerehabilitation if we convert the game into a rehabilitation exercise. And on top of that, we've already studied that how to use this MR-Link as a training device. So why don't we combine that with the telerehabilitation, and then we will be able to control the exercise intensity during telerehabilitation. And this will be a very helpful tool to improve the effectiveness of telerehabilitation. Also, this kind of semi-active device can be used in other than wearable robotics. So here is an example of how it might be used in robotic grippers. So robotic grippers have mechanical linkage systems, and the mechanical linkage systems, you can simply remove one of these links, and instead you put one smaller version of the MR-Link in it. And then you will be able to change the functioning of the entire mechanical linkage systems. If you use a series elastic actuator, you can only install it at the position of the actuator. But with this link, you can install it instead of any of the links to modify the function of the mechanical linkage system in a specific way that is suitable for your application. And lastly, so far we've only explored how to combine semi-active device with passive components, but it would also be possible to combine the semi-active device with active actuators as well. So take, for example, the pneumatic artificial muscles. With a regular pneumatic artificial muscle, you can control the stiffness of the muscle, and it has fixed damping. But there is wasted space inside of it that only contains air. So if you put one of these devices inside of it and connect the housing to one part and then the interaction rod to the other part, then you will be able to adjust the stiffness. You will be able to adjust the damping. On top of that, you will be adding a clutching mechanism to your artificial muscle. And as some of you know, you can only create impedance by connecting two muscles in antagonist arrangement. But with this setup, you might be able to do that without needing two muscles. So that's all from me. Thank you very much for your attention. I would like to acknowledge my colleagues and co-workers, and I'm happy to receive your questions.
Thank you very much, Professor Hassan. Okay. Any questions or comments from the floor?
Hi. Okay, you can hear me. Very inspiring talk. First, I have two questions. The first is that in your mechanism, because it's passive, so if you want to output force or power at some time, you have to harvest power at some other times, right?
Yeah, you can only produce force if you have harvested.
Yeah, so but for a patient, would that be a problem? Like if they have disabilities, would inputting power to the system be a problem?
Yeah,
like,
thank you for the question. It's a very good question. So you have to use it by understanding the dynamics of the task in which it is being used. So gate is a rhythmic event. It has cycles. So you can store energy from one phase of the cycle, and then you can release this energy in another phase of the cycle. But if you're not able to find these two cycles, the suitable periods from where you can store energy and release energy, it's not going to be possible just to use it. Because we're not asking the person to intentionally input energy in it and then later use it. We're harvesting the dynamics of the gate at some phase where braking is needed. At the same time, we store the energy in the spring. And then at the later phase, when it is needed, we release that to the gate.
Okay, thanks.
Thank you.
And the second question is, what's the difference of using the magnetic fluid versus like adding some kind of braking mechanism like cars? You know, like there are other braking mechanisms. Why use magnetic fluid?
There are other braking mechanisms, and some of them are much better at braking. But this one is a variable damper. It's not only a brake. So it's a variable damper. We can control the damping coefficient. And only when the coil current is high enough, it will clutch. It will become similar to a brake. And the force it's generating is kind of some form of friction force. Which might lead to think it's similar to a brake, but it's not. It's a variable damper.
Oh, okay. Thanks. I understand.
Thank
you. The magnetic fluid, I can understand that has more like more room for adjustments compared
It has
to
more
a-
room for adjustment, and we could embed components inside of it. So I could put the compression spring inside of the mechanism and create just one package that can be used in different applications. So this is another advantage, but it might be used with other systems. So there are other forms of smart materials. There are other arrangements in which you can combine semi-active and passive components. And I think some of them also might be very helpful.
Thank you very much.
Thank you.
Okay, thank you. Any other questions or comments? Please.
Thank you for the talk. Out of curiosity and own experience, how loud is the system when it's actuating the saved?
It's
machine?
not loud at all.
Okay.
Sometimes you can hear some resonance in the coil because there is a coil that is wrapped around the bobbin, and sometimes it works a little bit like a voice coil. It creates a little bit of some kind of small frequency, but it's really nothing audible, and it's way better than any other form of actuation. But one thing we had, like with the AFO, we could hear when the interaction rod was hitting on the foot segment, and that was a little bit annoying. But we can counter that. We can install some kind of cushioning device like PTFE on the tip of the interaction rod, and this way we might be able to eliminate that. But the device itself is almost silent.
Thank you.
Thank you.
Okay, next question, please. Yes.
Hi, fascinating talk. I just have one question. I see you evaluated on fatigue, the fatigue reduction on the patients, and especially as you go into like, what are other applications? Did you look into it all, like exceeding the amount of work that someone could do?
We haven't really looked into augmentation of the if that is your question, is that right? No, we haven't really, but it might be applicable in various other applications. But so far, we're mostly focused on assisting persons with some physical conditions, and later we might actually look into augmentation, but we haven't so far.
And just a quick second question. I might be misremembering, but you said the power added to some system like this is something like a battery. Conceivably, other energy sources could be added, like piezoelectric.
Myself, I'm not very familiar with piezoelectric, but
that's just an example. The scale I don't think is feasible, but other times.
Basically, what I was trying to say is we also have to think how large the battery is. So if you use a 100-watt motor to assist the person, it's gonna produce a lot of assistive force, but you're gonna need a big battery in order for them to carry around. And at that time, it's not gonna be really that much wearable. And this is why I think that we have this kind of dilemma in which we're using large actuators and large batteries in order to add more functions, but we don't see them so much in practice. In the hospital, everyone is using the passive and the semi-passive device because it's smaller, lighter weight, and more portable, and it fits inside their shoes or within their clothes. So this is the argument that I was trying to talk about, is it's going to be great to add a large motor, but we have to think how big and bulky it is and how much battery it's going to use. The MR-Link, it's not an active actuator, but it only needs 3.3 watts. So you can operate it with a small, like smartphone battery for almost all day long. And for me, that's a better way to implement a wearable robot.
Great. Thank you.
Thank you. There is one gentleman on the right side who has been waiting.
Okay, last question, please. Yes.
Was there any attempts or application to use this MR-Link for in a bidirectional way?
Bidirectional way?
Yes.
I'm not sure if how complicated that would be, but I will look into it definitely in the future. Yeah. I would like to not only receive from one end of the device and input at the same end. It would be more flexible if we can use both ends.
Okay.
Yeah.
Okay. Let's give a big hands for very informative presentation. Professor Modar.